All right, everyone, welcome, welcome. You are tuned in to the live stream for Boise State Physics First Friday Astronomy event. My name is Brian Jackson. I'm a professor in the physics department at Boise State. I'm very glad that you've joined us this evening. You're in for a real treat. For those of you who have never attended First Friday Astronomy before, this is an event that takes place on the first Friday of every month, hosted by Boise State Physics. When we don't have COVID, these happen in person, and we hope in the near future to be able to host these again in person. But for the foreseeable future, these will be online. So we're going to stream these events for the foreseeable future. But they're donated, donor supported, open to the public. Anyone is welcome to attend. We already have our fall guests lined up. Let me just show you that real quick. So I'm pretty excited about these. Here's our guest list for the fall. We have Professor Darcy Snowden from Central Washington University. She's going to come in and talk about Saturn's moon Titan. Dr. Laura Mayorga, who's from the Space Telescope Science Institute. Professor Barbara Ryden from the Ohio State University is going to tell us about time travel. And then we'll have Dr. Kathy Ulkin discussing the upcoming Lucy mission, which will visit 7 asteroids over the course of about a dozen years. So it should be a really great fall series of lectures. So, and these events take place on the first Friday of every month. So if it's the first Friday of a month, this event is happening. In the summer, we host these events at 8:30. Usually we host them later in the summer so that we can do stargazing afterward. Now we just host them later because we host them later. In the fall, the events will take place at 7:30. So 7:30 on the first Friday of every month, those will be our events. If these are events that you're excited by, that you enjoy, please consider helping to support the events. You can see the URL at the bottom here of the screen, boi.st/give-to-astronomy. And you have to capitalize those letters for some reason. And you can help to support these events. All right. And with that, I want to introduce our speaker for tonight. We are very fortunate to have Dr. Paul Verhage. Dr. Verhage is a local high school teacher, but he's more than that. He's a near space explorer and wannabe astronaut. I don't know why they haven't picked you yet for the astronaut corps, Dr. Verhage. You're definitely deserving. He did his PhD work on near space. The effects of near space experiments on student interest in science. And he found that these kinds of experiments where they launch balloons up high into the atmosphere and make measurements really spurred the student interest in science as a hobby. And hopefully that love of science as a hobby eventually translates into perhaps interest in science as a career. Dr. Verhage teaches currently at the Treasure Valley Math and Science Center, where he is actually famous. I have students who work with me who have told me about having him as a teacher. So he's actually very well known. And he's going to talk tonight about his work on suborbital ballooning. So I think you'll really enjoy it. I think I'm going to start your video here, Dr. Verhage.
Okay.
Perfect. There you go. Excellent. Okay, and it's all yours. Take it away.
Okay, great. Well, let me go ahead and start a PowerPoint presentation for you. I'll kind of walk you through what I'd like to talk about. And then I'll show you a short video taken from around 90,000 feet. So let me see if I can make this work properly. Let's go to my share screen, go to my presentation, and then we can start that. Okay, I think that's going. So Dr. Jackson, does that look okay to you? Okay, so I'm going to kind of follow the Mr. Montoya's way of introducing, a way to connect with the audience. So number one, I'd like to say is good afternoon or good evening. It's pleasant to be here. My name is Paul Verhage. And like many of you, I'm interested in space, but I find that it's a little too expensive to get there right now. The best pricing is around $10,000 a pound. I can't lose enough weight to be able to fly into space. So instead, I'm going to talk to you about how I explore a space-like environment. And I'd like to convince you that this is a place that you would like to explore also. So that's going to be my flight greeting, my name, personal link, and then manage the expectation. So I'd like you to walk away knowing more about Near Space. Also, by the way, I'd like to convince you that the most interesting place on Earth is accessible from any place on Earth. When I start getting really busy with Near Space, my life is this: I eat, I sleep, and I do Near Space. It takes a little time to set things up, but it's also so exciting that I don't care. I will spend time exploring Near Space and then looking at the data that I collect. And I'll show you what that data looks like. So a couple things. First off, I need to tell you where Near Space is, because that's not a term that most people have heard of. Some of you in the audience may have, but I'll be willing to bet that most of you have not heard that term before. Also, I'd like to show you what the conditions are like in Near Space. And when you see these conditions, you'll realize that Near Space really is a lot like outer space. It's far closer to outer space than it is to the surface of the Earth. Then I'll talk about how we get to Near Space and show you that's a very affordable method of getting into space. About $10 a pound rather than $10,000 a pound. A little bit about how we track these Near spacecraft and how you could track them also. So if you build an experiment, you could actually be a part of a chase team and go on the chase, track these Near spacecraft. You could act as a mission controller yourself. And then I'll give you a couple links for more additional information. So first off, where is Near Space? Well, there's a couple boundaries I need to describe to you first. First off, the International Civil Aviation Organization, and their representative here in the United States is the FAA, controls airspace. And we have controlled airspace that tops out at 60,000 feet, flight level 600 for you pilots out there. Above that, we go into Class E airspace. And at 60,000 feet, there's virtually no aircraft up there. Some military aircraft, I'm sure. Some military spy aircraft that I'm not allowed to know about. But I'm sure that there's aircraft up there. A few aircraft up there, but not many. A little bit above that, 63,000 feet is the Armstrong line. Now, this was discovered or kind of developed by a aeromedical, a doctor for the pilots, and determined that around 63,000 feet, the air pressure is low enough that your blood would boil, that liquids boil at lower temperatures as the air pressure on them drops. At 63,000 feet, the air pressure is low enough that liquids at body temperature, 98.7 degrees Fahrenheit, 37 degrees Celsius, will start boiling. So 60,000 feet is a good boundary for the bottom of the atmosphere of controlled airspace and the beginning of Near Space. Now, the International Aeronautical Federation, which sets standards for competitions and records, has set the boundary for outer space at around 328,000 feet, which is 61 miles or 100 kilometers. The reason why they set that, and this was discovered again, was developed from an individual who helped start the Jet Propulsion Laboratory. As you go up in altitude, the air pressure drops and your airspeed has to increase if you want to develop lift. At around 100 kilometers altitude, you have to travel at about 5 miles per second to develop aeronautical lift. And 5 miles per second is orbital velocity at that altitude. So once you get above 100 kilometers or 328,000 feet, you can no longer fly. You're actually at orbital velocity. So that's the boundary that the FAI sets for the boundary of outer space. So that region between 60,000 feet, the top of controlled airspace, and then your boundary for outer space is the region called Near Space. And the balloons that I fly get to around 100,000 feet. Some balloons I've gotten up to about 125,000 feet. The highest balloon I've heard of has gone to about 150,000 feet. So ballooning, the way that I get to Near Space, gets to about the bottom half of Near Space. Above that, you really need rockets to get any higher than that. As you would expect, the air pressure drops as you go up in altitude. And this is a graph that I created from data collected from one of my flights. And you can see on the very left, this balloon got to about 114,000 feet. and the air pressure was very close to a vacuum. In fact, at around 100,000 feet, the air pressure is 1% of the air pressure at sea level. So roughly 99% vacuum. If you look at this data and you did a little math on it, you'd realize that the air pressure drops by a factor of 1/2 for about every 18,000 feet. Now, that's not the way that a scientist or a earth scientist would describe that change. They would actually use something called scale height. And scale height is a measurement of how quickly the atmospheric pressure drops based on the number 2.718 or E. If you're familiar with your math, the number E. And if the air pressure decreases by a factor of 1/E for every 27,400 feet. And that's diagnostic of an atmosphere. Different planets have atmospheres that have different scale heights. And it tells you how quickly the air pressure drops as a function of altitude. It depends on the composition of the gas because of the different masses the gases have. The temperature of the gas, because that tells you how fast the gas wants to push away from the surface. And also the gravitational pull of the planet, which pulls the atmosphere back down again. But for Earth, that scale height is right around 27,400 feet. So every 27,400 feet, the air pressure decreases by a factor of E, or 2.718. And that's kind of the more accurate way to describe the way the atmosphere changes. But for us amateurs, describing by how it changes by a factor of 1/2 is valid, not quite as scientific. And it decreases by a factor of 1/2 for every 18,000 feet. And you can see that in this graph here. Again, which means that once I get to about 100,000 feet, 99% vacuum. The altitude at which the air pressure is the same air pressure as the surface of Mars is about 103,000 feet. So it's easy enough to actually send an experiment up to that altitude and test that experiment and see how well it would work on the surface of Mars. So it's a good simulation for Mars. Temperature decreases, as most people know, and if you go up in the mountains, it gets a little bit chillier. What most people don't know, though, is once you get above between 40 and 50,000 feet, the air temperature actually starts increasing again. And this is a really good experiment for students. You want to teach them about the atmosphere, the layers of the atmosphere. You know, the bottom is the troposphere, stratosphere above that, mesosphere higher than that. As you go up in the troposphere, our lowest layer of the atmosphere, the air pressure decreases as we expect. But somewhere between 40 and 50,000 feet, and it depends on the time of the year and your latitude, the air temperature actually starts increasing again. Now I could teach a student that the stratosphere starts at around 40,000 feet and that it gets warmer in the stratosphere because ozone is blocking ultraviolet radiation. That ultraviolet radiation is a source of energy. You can't destroy energy. So the atmosphere has to do something with that energy and it converts it into heat. So it warms up the atmosphere. Once a balloon rises above 40 to 50,000 feet, the air temperature increases because the balloon is traveling through the lower part of the ozone layer in the stratosphere. Now I could teach a student that the stratosphere starts at around 40,000 feet and the air temperature goes up. And I'm sure that he or she will remember that long enough to take a test. But if I had a student design an experiment to measure the air temperature, launch a weather balloon for them, they get the data, they analyze it, and they see this really amazing thing where the air temperature starts changing dramatically around 40 to 50,000 feet. I'll bet you they'll remember that for a lot longer. And years later, they'll remember, oh yes, the stratosphere starts at around 40 to 50,000 feet because that's where the ozone layer is located. And that ozone layer is blocking ultraviolet radiation and converts it into heat, warms up the stratosphere. So that's kind of an interesting experiment to do and an interesting thing to see as a result of your balloon flights. Relative humidity, you know, how will the relative humidity change? I don't know if there's any way that you would normally think of how it would change. Well, we plot the data, we'll take a look at it here, and you'll see that the relative humidity does decrease, but there's some spikes along the way. Those spikes are where clouds are located. So in this graph here, around 5,000 feet, there's a spike because we passed through a cloud layer. And then around 26,000 feet, there was another spike because we passed through a second cloud layer. The second cloud layer would be cirrus clouds because it's cold enough that it would be ice crystals. But I can see in this graph that there were two cloud layers that we passed through. But literally, once we got above 10,000 feet, it got very, very dry. And if you are into infrared astronomy, you'll know that those observatories are at very high altitudes on mountaintops because they get above the water moisture in the lower part of the atmosphere. And a balloon experiment like this, you can see why you might would put an infrared facility at really high altitudes. It turns out that infrared does block a lot of humidity blocks a lot of infrared from stellar sources. And in fact, it's that heat and humidity in the Midwest that makes the nights so warm because you just can't get the energy, the heat out of that moisture, that humidity. It's actually a greenhouse gas, really. But once you get above 10,000, 15,000 feet, we get into a very dry part of the atmosphere. And that becomes a really nice place to do experiments if you can hold your telescope still. And I'll show some video here around 90,000 feet, and you see that things don't hold still. So there's a lot of engineering that goes into flying observatories on weather balloons above, above 20,000 feet. But if you can accept, good visibility, but not perfect infrared visibility, high mountaintops work really well. And you can see that in this data. Cosmic rays. Now, this is my interest, my greatest interest. And I knew that as you go up in altitude, there's more cosmic rays. In fact, if you go back to about 1912 to the discovery of cosmic rays by Victor Hess, he actually went up in weather balloons, and these were hydrogen-filled weather balloons. And if you remember the Hindenburg story, this guy was taking a big chance to send radiation detectors up with him. And I believe he got as high as 35,000 feet, which is very dangerous altitude because of the low air pressure. But he discovered with his radiation detectors, which were basically glorified electroscopes, that the amount of radiation increased as he got higher and higher. That told him the source of this radiation was not the surface of the Earth. It wasn't, uranium and thorium in the crust. It actually was coming from outer space or cosmic sources. He called it cosmic rays in that case. The thing that really got me on my first flight, almost 24 years ago, is once you get above 62,000 feet, the cosmic ray count decreases. And this threw me for a loop. Is what is going on? These cosmic rays are coming from outer space. There should be more and more of them as we get above the atmosphere and the atmosphere stops blocking them. Well, it turns out I learned a lot, and that is that cosmic rays, when they enter the atmosphere, are called primary cosmic rays. They'll impact oxygen and nitrogen molecules. They'll shatter those atoms, creating secondary cosmic rays. Those secondary cosmic rays, and there can be 100 of those for every primary cosmic ray, are what we detect here on the surface, and they get filtered out as you go lower and lower in the atmosphere. Once they get above around 62,000 feet or so, there's fewer collisions because there's fewer gas molecules, and I'm detecting more and more primary cosmic rays. That boundary where the cosmic rays start decreasing is called the Flotz line. And as far as I know, it's around 62,000 feet from my data, but I'm actually detecting primary cosmic rays or cosmic rays from outer space, not the result of cosmic rays shattering molecules in the atmosphere. What I find really fascinating about this is that the Geiger counter I send up can actually count each cosmic ray. And you have to think about, where do cosmic rays come from? Some of them come from the sun, some of them from supernova explosions. Some of them are high enough energy that may actually come from other galaxies, say active galactic nuclei or something like that. When my balloon is at high altitude, above 62,000 feet and higher, and I start detecting cosmic rays, I'm actually counting atoms that originated from another star. So this had to travel for light years and light years to get here, years and years to get here. But it's actually atoms from another star. These are not from our solar system. Again, some of them are from the sun, but I'm starting to count these actual atoms from another star. And I don't know of any other way I can do that except by doing a high altitude weather balloon launch. This is what it looks like in near space. This picture is taken around 86,000 feet, and we're so high that the air pressure is down to only a few percent of air pressure here at sea level. Now at sea level, when you look up in the sky is blue. That blue light is actually blue from the sun. Something called Rayleigh scattering The molecules in the atmosphere are roughly the size of a blue wavelength of light, and blue light is preferentially scattered by the molecules. So no matter where I look in the sky, I'm seeing blue light from the sun, even if I'm looking directly away from the sun. But you get above 85,000 feet or so, the air pressure is so low, there are so few molecules, you're no longer scattering sunlight from the sun. So there's no blue skies, it's black skies. I'm saying the black of space. Where I do see the blue atmosphere or the blue light from the sun is below the balloon when I look down at the Earth. I see a blue marble below me, and that's the sunlight that got scattered out, and it gets scattered upwards, downwards, sideways, all directions. And that's where I'm seeing the blue light. Also in a picture like this, if you get a camera that's not a wide angle, because wide angle cameras will distort the view. But you could put a ruler against a picture like this and you can actually measure the curvature. You can actually see the Earth is curved. So those people that tell you that the world is flat, I have a balloon ride for them to about 85,000 feet, just so they can see what this really looks like when you get that high. But it really is curved. And not only that, but as you get higher, you're looking over the edge of the Earth. You're looking down over the edge of the Earth. Because that happens, we have something called horizontal depression. It actually lowers the edge of the atmosphere. At 100,000 feet, the horizon is about 5 degrees lower than it is when you're at sea level. So the sky is actually 190 degrees around and only 170 underneath you. Now, as you get higher, like in the space shuttle, the International Space Station, you're high enough that that actually gets depressed even further, and you have now a smaller globe Earth. Go to the moon, and now you're looking at roughly half the Earth, and horizontal depression is, tens of degrees at that point. You're so far away. But in a balloon at 100,000 feet, horizontal depression is 5 degrees, and actually can measure the curvature of the Earth. And in fact, whereas we're looking over the curve of the Earth, that at around 100,000 feet, I can see 400 miles away. Now, a 6-foot tall adult sees roughly 3 miles to the horizon if it's flat. Mountains and things will extend your distance. But at 100,000 feet, you see about 400 miles. So the balloon could go up, take one rotation in about 1 minute, and see the entire state of Idaho, a good chunk of Washington, Oregon, Nevada, Wyoming, all these different states as you're looking around. So it's really kind of cool to send a balloon up and see pictures like that. And I mean, what's really nice about this too is, back in the 15 years ago, back when you go to the photo lab, the 1-hour photo lab, I actually turned in some pictures like these to be developed. And the photo lab technician asked me if I was an astronaut. And because there's just no other way you're going to get pictures like this unless you happen to be an astronaut. Okay, how do I get to near space? This is an old graphic because it says helium. The helium reserve has been turned over, and where the United States is not saving helium like it used to, so the price really fluctuates a lot. In fact, helium is probably 5, 6, 10 times more expensive than it used to be. I use a hydrogen-filled weather balloon now. And since we're filling outdoors, no one smokes, the balloons have no air inside of them. They're vacuumed out, so they can be packed up and folded up pretty tightly for shipping. It's pure hydrogen in the balloon, no oxygen. It's not going to explode. If you were to burst the balloon, the hydrogen would quickly rise and mix with the atmosphere and not be a problem. And even if you tried to light it on fire, there would be a fireball that would go up quickly, and there would be no explosion. So it's not very dangerous to actually fill with a hydrogen weather balloon, a balloon with hydrogen gas, as long as you're filling outdoors. You fill indoors, all bets are off. That's a dumb thing to do. Don't do that. So we'll fill these weather balloons, and the balloon, it weighs about 2.5 pounds empty. So think of a huge party balloon. And this balloon will be about 7 feet tall when I fill it with hydrogen gas. Hook a load line onto it. It's about 20 feet. And that keeps the balloon, once it bursts, keeps it from falling on the parachute. Sometimes I use a cut down, and that just cuts the balloon away from the parachute. Most of the time I don't do that. The parachute is a parachute that I've made. I sew them. I'm not a seamstress, but I can do technical sewing and sew a parachute. And I've sewn probably 6 parachutes that have worked up to 124,000 feet. I wouldn't trust my life on it, but I'd be perfectly fine sending up my experiments on them. The spreader ring beneath the parachute just keeps the parachute from twisting as the balloon goes up, because I want to make sure that when the balloon bursts, that parachute's ready to open up immediately and not be twisted up and can't open up properly. Tracking modules, this is using amateur radio, and I'll talk a little bit about that here in a little bit, but there's a GPS receiver and amateur radio on it. And I have an amateur radio license, a KD4STH, general class license. You don't need to, you could be a technician's license to do this. And there's ways to actually track them without an amateur radio license, as I'll talk about. But these tracking modules will tell us the location of the balloon every minute. So every minute I know its long and its altitude. I know its heading and I know its speed. So I know exactly what this balloon is doing every minute throughout the flight. Beneath the tracking modules, we'll send up the balloon satellites, stratolites, or balloon sats. And those are experiments that students can design. And they can put experiments inside of it. It's literally a styrofoam box. Styrofoam box is lightweight, lots of insulation, keeps the experiment warm, and very easy to build. There's not a lot of machining involved with cutting and hot gluing styrofoam together and then putting tape to close it all up. So the students can build their experiments, test them on the ground, and then I literally just tie them to my tracking modules and we send them up into Near Space for them. And then they can track them. This is a big beast. This Near Spacecraft is anywhere from 30 to 50 feet tall. It's about, so think about 40 feet tall, close to the height of a 4-story building, but only weighs 12 pounds. Now I can put more weight on these. In fact, I've launched a 32-pound phonograph record for Third Man Records several years ago, 4 years ago, so they could play a phonograph record in Near Space. It took FAA permissions to do this. But as long as I'm willing to fly 12 pounds or less, I don't need any special permission from the FAA. I file a note and let the pilots know we're launching and we're good to go. We climb at about 1,000 feet per minute, and sometimes faster. So we climb up and we are very busy on the way up. We don't dawdle around. We get up to altitude as quick as we can and can get higher than 100,000 feet. My average is about 88,000 feet. My highest has been 124,000 feet. My lowest, unfortunately, was 8 feet when the load line got separated from the balloon and the rest of the Near Spacecraft. So we did get 8 feet on that flight, but it didn't last long. We didn't go very far. But typically, out of 200 flights, I've gone to 88,000 feet on average on 200 flights, and only lost 2 flights. 1 flight lost, 1 flight stolen. So 99% success rate. Can't complain too much for that. Tracking now is done with, this is amateur radio, it's called APRS, Automatic Packet Reporting System. It has a GPS and a TNC terminal node controller. Terminal node controller is a modem for amateur radio. And then we hook it up to a radio, amateur radio. So 3 pieces put together, the GPS puts out a position every second. The TNC will listen to that sentence data from the GPS once a minute, key the transmitter, and then send the GPS data back down to the ground in a special format called APRS. And then on the ground, I use my APRS radio that has a built-in GPS receiver. It compares the data from the tracking modules to the radio and will tell me what you're tracking is this distance away, this altitude, and if you look out to the left at a 45-degree angle, there's the balloon. And we've used that data. We've actually seen the balloons at 100,000 feet because the radio will tell us where to look. When the balloon bursts, we parachute down and we go chasing after it. It'll tell me where I need to go. It'll say it's straight ahead or it's off to your right. You're 2 miles behind. Or it'll tell me it's coming down through the jet stream at 60 miles an hour. You're only going 25, past CUNA. It's going to get ahead of you before it gets to the ground. And typically, we're in the area when it comes down because we'll look at weather predictions for winds aloft reports. When we'll have a good idea of where the balloon's going to go, what its flight path is. And we can actually launch on a day and a location that lets us get near the landing site before the balloon comes down. It's about 90 minutes up, 45 minutes down. As long as we don't hit the jet stream going at 120 miles an hour, which has happened before for me, we can actually be in that location when it comes down. Now, amateur radio operators they're a kind bunch. They like to help people. So they set up internet gates or iGates. And this actually takes data from the APRS system, which if you're not an amateur radio operator, you can't look at directly, but puts it on the internet. And I'll show what that looks like. But using the internet, you go to two different websites on your cell phone, put in the correct call sign, and it actually brings up Google Maps and will actually show you where the balloon is using your cell phone. And now students who are not amateur radio operators can actually track the balloon live. Every minute their cell phone gets updated with a map of where the balloon is located. And they can follow along and follow their experiment. I've used this to launch experiments for students that were not in the state, for students in other states. In fact, I launched for some students in Australia several years ago, gave them my tracking information. And those students in Australia were able to track the balloon live, halfway, literally halfway around the world. So it's pretty cool. This is an example of a website. This is APRS.fi. And this has my call sign and shows you the location of the balloon. And you can see the blue path showed you what the balloon did. Now, this is the last half of the balloon flight. I would need to change some settings on the website, and I could track the entire flight. And you'll see the balloon went up, turned around, and then on the way down, changed directions again. But you see also we landed outside the birds of prey. I landed southwest of I-84. But we were able to track the balloon, and you just go to this website and you can zoom in, you can click the icon and it'll tell you the altitude, its speed, its direction, tells you everything about the balloon and what it's doing. Some of my trackers will actually give you the temperature and the battery voltage, so you can follow that also. Which is interesting because if you see the battery voltage is dropping down way too fast, we may have a problem getting the recovery. So I always send up two trackers just to make sure. And I send up fresh batteries so that won't happen. But I've had one flight actually stop transmitting on the way up, and I don't know why, but that was one of the two flights I lost. But this is what it's like to track a balloon and just using this system on your cell phone and literally go on chase and follow what the balloon is doing with your experiment. I'm going to show you some pictures. This is what it's actually like to fill a balloon and do these launches and see some images and data from them. So this was a summer camp. These are students, these are junior high to high school students who built their experiments in teams of 4, and we're now filling the balloon. This is with helium, because this was with the school. The school was willing to pay the extra money for the helium. Couldn't convince them the hydrogen is safe, but they were willing to pay for the helium, and that's fine. I will fly with helium if somebody will pay for it. So we have one of the students actually filling the weather balloon. Now we're raising the tracking modules and the parachute. We raise these one module at a time, and then we can release them. And then this is the most beautiful sight in the world. You watch this balloon take off. And you can see the balloon is, this is literally a 40-foot long chain of experiments going up on a weather balloon. Got the weather balloon, the parachute, 2 tracking modules, and then 1, 2, 3, 4, 5, looks like 6 different experiments going up on this weather balloon, and it is just a beautiful thing to see happen. Then we go chasing after the balloon, and we'll use amateur radio to chase after it. And usually we'll stop someplace, get some gas, restroom breaks, some snacks or something like that to eat. So it's really kind of cool to pull into a gas station, especially when you have out of state or out of county tags on your car, and you've got these antennas all over your car. And just really makes people wonder, what's going on here? Are you with the federal government or something like that? And then they also will see us looking up in the sky. And they'll look up, it's like, what are you looking at? Unless you know what you're looking for, you don't see the balloon. The balloon looks like a little star in the sky. If you know where to look, you'll see it. If you don't know where to look, you'll never find it. So they'll look up and it's like, what the heck are you people looking at? And then we'll kind of, get them next to a telephone pole or light pole or corner of a building and say, okay, now look at the corner, look for a star, just off the edge of the building, and they'll see it. Then take them over to the tracking vehicles, the recovery vehicles we have, show them the laptop, and they can actually see live data coming down from this balloon that they're watching. The ultimate is you watch that balloon and suddenly over about 1 second, it disappears. When that balloon disappears, that meant it burst and it's time for recovery. This This is the second most beautiful site that I can think of. And that's where you walk out to a field and there's your Near spacecraft laying in the grass where the tracking module said it was located. And there it is. This thing went, 60 miles, reached 100,000 feet, and you may have even seen it land. And you walk out to a field and there it is. It's right there where you expect it. It's a beautiful thing to see. We have to watch out with students when we finally get these to the recovery zone, because we've had students just literally kick the doors open on the vehicles and go running after their experiments. Just got to make sure it's safe, that they don't run across the street when they're doing the recovery. It's very exciting at the very end. This is an example of some pictures taken from a flight. And on a balloon flight like this, let me tell you, we can see your backyard, okay? We can see, now we don't spy on people, but the balloon goes up and we're looking at a tracking module below the camera module, and we're seeing people's backyards, their front yards, everything about their yards as we're going up. This is around 50,000 feet above an airport in Lawrence, Kansas. And we are seeing the runway, the tarmac, all that. This was a really unique picture. We sent out multiple balloons and 2 of them went up at exactly the same rate, launched at the same time, and they followed each other. This is at 50,000 feet. Then the camera was taking pictures sideways and it spins around, takes a picture, and it caught a picture of its neighboring balloon on the way up. To give you a sense of scale, the orange module near the bottom is a 1 foot cube. So that balloon, it started out about 6 feet wide, 7 feet tall. And if you look at that cube, it is probably close to 10 to 15 feet wide. That balloon has expanded a lot as it's gone up in altitude. Again, around 50,000 feet. Here we are above 30,000 feet. We're looking down, seeing contrails of aircraft below us. This was another one I launched, and this was an experiment I launched. And we're looking at farm fields. We're looking at an entire town on the left in Kansas. This was in Kansas, near Hutchinson, Kansas, a small town near Hutchinson, Kansas. And we're actually seeing farm fields below us, the town. And then you see 2 balloon sets, a black cube and another one that's a framework. So not all balloon sets have to be styrofoam cubes. You build them to operate the experiment that you want. You build them to specification. Another one here, this is above the Platte River in Nebraska. We've got this muddy Platte River with branches throughout the river. And it's hazy day, so the ground is blue, but it's also kind of hazy blue. This is the Midwest, and during the summertime, humidity is its middle name. It gets pretty vicious out there with the heat and humidity. This was a flight actually in Idaho, in the Treasure Valley. Those clouds are forming over the Owyhee mountain range. There's air mass moving in from the south. That air mass has moisture in it, hits the Owyhees, it's forced to rise. It's called orographic lift. And when it's forced to rise, you get condensation that drives this convective cloud development. And we have these cumulus clouds that mark the edge of the Owyhee mountain range. Off to the left, it's hazy because that's smoke filling the valley, Treasure Valley, the Western Treasure Valley here. So we're actually looking down at the smoke filling the Treasure Valley. We would normally see the Owyhee mountain range except for the smoke. This case here, I sent up a thermal imager. So it's a long wave infrared imager. It takes heat map pictures. And then on the right is actual color camera taking pictures. So this is the Snake River, 2 islands in the Snake River. And the left shows the thermal image that was taken at the same time. And you'll see that the river is warmer because it's yellow than the land, which is a purple to a blue. Let's see if I can point this out. There's this white spot right here. That's right here. These are buildings. The buildings are cooler than the fields around them. Also, you notice that this is irrigated. It's cooler. It's not irrigated here, and it's warmer right here. So we are actually got these thermal maps, and we can tell you something about the land as far as temperature goes based on these temperatures. And we can detect, like I said, the presence of some, probably a metal building at this point. But it's interesting to take these thermal images and compare them to what you see. the contrast allows you to understand more about what you're looking at. It's kind of like a poor man's spectral imaging, and you learn more about what you see based on multiple wavelengths of light that you're looking at. In this case here, we're above the clouds, and the clouds are cold. And the reason I know they're cold is they're black, dark blue and black dots or splotches. Those are the clouds, and they're intensely cold compared to the ground below them. My most interesting imaging comes from near infrared. Now, near infrared is just beyond the red to the beginning of infrared. And remember when I said that the sky is blue because the oxygen and nitrogen molecules preferentially scatter blue light. Well, infrared is about twice as long as a blue wavelength of light. Therefore, the atmosphere does not scatter infrared. So if this is a picture looking at the horizon, and I made this in black and white because infrared or near infrared has a really weird color palette if you had it on a digital camera. So I tell the camera to go to black and white or else the colors get really kind of freaky. In this case here, the near infrared light is emitted by the sun. It's bouncing off the ground, going through the atmosphere, and it's not being scattered by the atmosphere. If this were an image in visible light, the horizon would be a blue haze and you wouldn't be able to see a lot of detail. Infrared, I have very sharp detail on the ground because that light is being reflected off the surface and not scattered. It's straight line path from its point of reflection to the camera. So we're seeing about 280 miles away, and I can see there's mountains, I can see there's crinkles and valleys and things like that in the mountains, literally 250 miles away that you couldn't see in visible light. So near infrared is almost like stripping the atmosphere off of the Earth and seeing the Earth as it is, the surface of the Earth as it is without the atmosphere mucking up your view. Let's see, next one I'm going to take a look at this is looking down in near infrared. Now, what's interesting about this one, and since we don't see near infrared, people aren't familiar with this, but chlorophyll is green, not because it absorbs green light, but because it absorbs red and blue light and then reflects the green. But it turns out that chlorophyll also will reflect near infrared light. So looking down in this picture here, looking straight down, and this is the Snake River below us and some rivers there. To the north of it is farm fields. Those farm fields have plants, they're healthy, they're very green, and they're emitting or reflecting, not emitting, excuse me, they're reflecting a lot of near infrared from the sun. So the farm fields that still have crops are very bright white. Those where they've been cut are very dark. So let me point out, for instance, right here, here's a farm field. This has got a lot of plants in it. It's very green. This one here has been cut and there's mostly dirt there or it's just stubble and there's not a lot of chlorophyll. So it looks very dark. Turns out that rivers, or bodies of water, this is Lake Lowell, will only reflect near infrared like a mirror surface. So unless I'm looking down at that surface and then reflecting back up to the sun, the bodies of water are black because they're reflecting near infrared from the sky. And remember, the sky is black in near infrared. So all I see is these looks like black ink puddles. Those are rivers and lakes in this case here. Okay, now I'm going to show you some video. This video is around 90,000 feet, shows the burst of a balloon, and you'll see what it looks like if you were up there. I would definitely recommend that you your seatbelts on if you're up here near space when it happens. Okay, let me stop share. Okay, and then do share screen again. Go to the video. Okay, so this is a flight 2 years ago. GPSL was a Great Plains super launch. And this is a celebration this is a bunch of amateur radio operators who do these balloon flights for themselves and for students. It's a conference, annual conference, and it always ends with a mass balloon launch. And I wanted to celebrate. This was done, the first GPSL, the first Great Plains super launch done in Idaho. So not technically Great Plains anymore, since Idaho's not the Great Plains. But it was kind of a celebration we did. We had a flight out here. Really nice GPSL. We had people at the wineries, and then we did conferences, then we did the balloon launches. So I'm going to show about 2 minutes, and this will be about a minute before the burst and about a minute after the balloon burst. The camera is looking out through a styrofoam box. So on the right side edge, it's black because I didn't cut the opening wide enough for the camera. So kind of vignetting on the right side there. The flight on the way up, once you get high enough altitude, it's very gentle. The stratosphere, there's not a lot of wind. Things tend to be, or there's some wind, but tend not to be a lot of turbulence. And it tends to be fairly peaceful up there. Now you're gonna see something white kind of dance across the sky right there. That's the moon. We are seeing the moon. It would be a gibbous moon at this rate, during this time. And you'll see that we have a black skies. The atmosphere is a blue band above the edge of the Earth. The Earth is curving really weird directions because this is a wide angle camera lens, and you can't trust what a wide angle camera lens tells you about curvatures. And without as much atmosphere above us, only about 2% of the atmosphere that we normally would have, 3%. The sunlight's much more intense, and there's also a lot more ultraviolet radiation. You would get a sunburn very fast up here compared to the ground. Okay, there was the balloon burst. And you saw bits of the balloon, bits of the parachute, and you'll see that we are coming down, and it is crazy for the beginning of the descent. Part of the reason why is there's just not a lot of atmosphere. The parachute is opened, but the balloon has to fall probably 8 or 9 times faster just to feel the same amount of drag as it would on this, closer to sea level. So it gets really chaotic for the initial part of the descent. Near the ground, it's not nearly so bad. See, Mr. Potato Head is holding on only by the sheer luck of these carbon fiber rods. I don't know if you've ever seen the movie Planet of the Apes, the beginning when the APRS spacecraft is re-entering Earth's atmosphere, it probably looks and felt a lot like this. So that's kind of what it's like to start with during, when you're up there, when balloon bursts and you're on your way down. Okay, do a stop. And stop share. Let me go back to share screen. And bring up my PowerPoint. Okay, and then slideshow. Okay, and I think I need to go. Okay, there we go. So now this is an example. Now we have still cameras taking pictures of the ground or the horizon, but it gets really chaotic on the way down, and payloads will swing around like mad. In this case here, we lucked out on these two different flights. The camera module got whipped around high enough, it actually took pictures of the capsules during descent, the Near Spacecraft during descent. In this case here, the balloon completely shredded and we have very little balloon left. But on the left, the balloon popped, brought most of the latex back down with us. This descent will turn out to be a little bit nicer because you don't have a lot of weight on the end pulling on the parachute. This descent is going to be a lot rougher because you've got about 2 pounds of latex on a 20-foot line, just whipping the parachute around and making the descent more chaotic. But it was interesting to see that, right after burst, these things are opened up. In fact, this one is right after burst, and you see that parachute is fully opened. It takes within a second, the parachute's opened. And then if you're lucky, and a lot of times we have been, where the balloon's going to come down, and we were at the landing site, looked up, and this is on a smoky day. There was fires in the valley, but we looked up and we could see the parachute coming down. So there it is. We're out of our car. There's students with us looking up. There's this parachute. This thing's been to 90,000 feet, and we're seeing the payloads come parachuting down again. So really it's a fun sight to see. And actually, this is probably the most dangerous part of the chase. Because everybody wants to get out and go run after the balloon and be there first, and that's a recipe for an accident if you don't settle down during the chase. For some more information, you go to my website. I have my 200 flights are there. Go under the amateur radio high altitude balloon link at nearsis.com, and you can actually see the data from past flights. And it's set up in a spreadsheet. There's some pictures. Feel free to copy and analyze the data any way you'd like. I'm not currently active with YouTube anymore, but I've got some past videos from balloon flights. I will get back to that again. With the COVID-19, I'm not blogging as much as I used to either, but again, this shall pass. And then you can go back to my blog spot and you can see some reports I put out on balloon launches. And then I'm more active on Twitter right now. So if you're interested in near space, there's information there. If you're interested in some other activities I do, there's a lot more that I do than just near space. And you'll see that on Twitter also. With that, I think I'd like to see if there's any questions. I'd like to thank you very much for attending this presentation I've given. I hope I've convinced you that the most interesting place on Earth is accessible from any place on Earth. It's only 10 to 20 miles above your head. You can get there for about $10 a pound. You don't have to be an amateur radio operator, although it does help, but there are people that will help out if you're not an amateur radio operator. And thank you very much.
That was awesome, Paul. Thank you so much. That was really great. Yes, we have a couple of questions here.
Okay.
Yeah, some really great questions. So Dustin asks, what is the nominal battery life with your radios that you use for telemetry?
Okay, so battery chemistry is very important. People don't think about that. They think, well, I got alkaline batteries or lipo batteries or something like that. The different chemistries behave differently depending on the temperatures. And we can get temperatures as low as minus 90 degrees at the beginning of the stratosphere in the wintertime. And I can guarantee you that an alkaline battery does not like that. With the trackers I have, I can put either 1 or 2 AA lithium cells in them, depending on the tracker. That'll handle the cold temperatures. Although for security, I'd like to put a little hand warmer on top of the battery and run the hand warmer about an hour before we launch, just to get a little extra heat. But experiments inside batteries inside of a styrofoam box do stay warmer. They get down to about freezing, so 0 degrees Celsius or 32 degrees Fahrenheit. You're not exposed directly to the air. But battery chemistry is important. Lipo batteries, use lithium as your best security. Don't use alkaline if you can help it, and don't use alkaline on something that's critical. Especially if it's exposed to the air, your alkaline battery is going to have a heart attack and die on the way up. And I'll tell you, being at 100,000 feet and not being able to track your balloon anymore is like the worst feeling you're going to have.
Yeah, and then Dustin also asks, I think he's asking, do these experiments take, is it just one day? Are you talking about over multiple days?
Okay, good question. So the balloons I send up are latex balloons. They'll rise for 90 minutes, they'll burst, and we parachute down, and we're on the ground in 45 minutes. In that time, we can travel, 40 miles on average. So it's about we're talking about a 2-hour flight or so. That's about as long as we have to run. Now, there are zero pressure balloons made of polyethylene, and those don't burst. They can actually reach a maximum altitude. They become neutrally buoyant, and they'll actually float up there for quite a while. And those, you definitely need to think about your power sources for that. For those balloons, you have to actually cut them down. So you need a cut down device, and also a device that terminates the balloon envelope. It's a much more complex engineering problem that has to work at near vacuums at freezing conditions. So it's a much more difficult system to design, but people do that. There are some balloons that people launch. These are Mylar balloons. They won't burst, but they only get to about 30 to 40,000 feet. But those balloons have actually gone around the world multiple times. And batteries you can't do that with batteries. So they send up some very lightweight, high efficiency solar cells. For about $100, you can buy one of these trackers if you have an amateur radio license, and then spend about $3 for the balloon and literally pennies for the hydrogen. Launch one of these balloons. You don't get any data from it because you can't, they're too lightweight. You have to minimize your weight and you just can't send up much. But you can track the position, which tells you could get wind speed and direction at those altitudes. You can certainly get that, but not much more than that. And these can go around the world multiple times.
Oh, that's really fascinating. JL Cop, I don't know who this person is. JL Cop asks, how much practical difference does hydrogen make instead of helium for lift?
So about 8%. About 8% more lift. So what that comes out to altitude, probably a few thousand feet difference. The big problem is that the balloon, or the issue, not a problem, but the issue is that the balloons, when they're manufactured, are not consistent from one balloon to the next. So you may get a balloon that's got extra thick latex and might get at 5,000 feet, or one that has a thin patch and might burst 10,000 feet early. So in a practical sense, probably not a whole lot, because you can't guarantee the balloons are going to can reach maximum altitude anyways, but it does lower your cost significantly. I can get a tank of hydrogen for about $70 and a tank of helium probably about $200 to $300. So it makes a huge difference in how many times I can fly, but it's 8%. If you do the math, look at the weight of the gas, 1 liter at standard temperature and pressure compared to the atmosphere, you get about 8% more lift. That's a good math problem for your chemistry students to do, by the way.
Yeah, that's really interesting. Somebody asks, what would be the worst place for it to land, and aren't you worried about that?
So the worst place would be some tall mountain that's heavily forested and there's no roads. So, and the reason we avoid that is that the National Weather Service launches 100 balloons across the United States every 12 hours. So about 200 balloon launches a day. Those balloon launches are not meant to be recovered, although some of them do get recovered. But they give the National Weather Service the wind speed and direction at different altitudes. And then they can use that and put that into a model of the atmosphere, and they can predict what winds aloft will look like, say, 3 days from now. I use that data, and then I can actually predict the balloon flight. And I would actually look at, if we're going to launch this Saturday, I expect the balloon to climb at 1,000 feet per minute. I expect it to go to 90,000 feet, feed that into a website, and it will say, here's the path of your balloon, and we'll show where the balloon's going to land. And then I can say, oh, that's not a good place. Let's go travel an hour further away, change my launch location, see where the landing site is. And I'll make sure that I pick a launch site that has a good road between the launch site and the landing site. And it might take us an hour. I've had to go to Jordan Valley. It's a 45-minute drive from where I'm at to do the launch. But the recovery is, we're landing near Cuna. So it's high-speed roads the whole way until you get into town, slow it down. But you can be there in less than 2 hours, and you can be there waiting for the landing. And we've actually gone to the Paul's Market in Cuna and just watched the balloon, and we're just watching on our radios for this thing to burst. So run your flight predictions, double check them, and then be prepared in Idaho, because it seems more often than not, the winds go across the valley. They don't go along the valley for some reason. We have to launch someplace else. And I've had to launch from Rome, for instance, Rome, Oregon. Other times we've been locked under a high pressure dome, and the balloon hasn't gone very far. I've had one balloon in Kansas go only 4 miles, which meant I could have launched it, walked to the landing site, and then picked it up. But instead we went out to breakfast and then went to the landing site. So yeah, look at the weather predictions, and you can make sure that you're not going to end up at a bad place. But literally the worst place would be in Idaho is tall mountains, forested, and there's no roads up there.
Yeah, that's really fascinating. I have a question. I don't know, maybe this is a little technical, but some of the plots you showed, I was interested to see how the measurements you were making, especially at very high altitude, started to become really, really ragged.
Sure.
And
that's the relative humidity sensor.
Yeah. And it's not, are you really seeing like waves, or is that just instrumental?
I think it's instrumental.
Yeah.
It doesn't handle low pressures well, and you get sunlight on the sensor, and it acts up. I think it just doesn't handle low air. It's designed for near ground sea level air pressures, and when you start putting in a vacuum, it just goes haywire.
Doesn't like it. And I noticed also that the one plot you showed, that the relative humidity kind of bottomed out at about 10%. And I was kind of surprised by that. Are these calibrated so that you can make measurements at that level, or is that just sort of a calibration issue? I would have expected it to 0.
Yeah. So again, the sensor is calibrated for around sea level pressure, and at high altitude, we can kind of look at the magnitude change and get some qualitative idea of what's going on. But to get really accurate measurements, it's most accurate when you're close to the ground, and less accurate, more of an issue as you get higher. But that would be a good experiment for students to design and then work on the calibration. It may be just a math change. They say with this pressure sensor, this is the math you need to analyze the pressure, the relative humidity. But if the pressure changes, maybe you need to change things a little bit. But again, they're not designing these for what I'm using them for. So it gives us a good idea of what's going on, and it does show us qualitatively what happens, but also low altitude, it does show us, it's 100% relative humidity as you pass through a cloud, as you would expect.
Yeah, that's really fascinating. Okay, we have one other question on here. It's asked, what is the most interesting student experiment that you have launched?
Oh my gosh. Okay. So one of them was in the early days, I was really worried about experiments working and holding things onto the capsule because it's very cold up there. I found out that zip ties, for instance, will break in near space because it's too cold. And you put any stress on them, they break. So the question I had is, could we use rubber bands to hold hatches, lightweight hatches onto to capsules and experiments? So this is a 4th grade class. I gave them a piece of stick, gave them some black paint and some aluminized mylar. And they actually took the stick, half black, put half in aluminized mylar, got identical rubber bands, different types of rubber bands, thick versus thin, different colors and all that. And they wrapped them on this dowel on the stick, the same on one side as the other side, black versus shiny silver. And we launched that up to see if those rubber bands would hold up in those cold temperatures and the increased ultraviolet radiation and increased ozone. And we found out the rubber bands did just fine. And because of that, if I have a lightweight hatch that I have to hold on to the capsule, I know I can use rubber bands. And that's a 4th grade class that figured out you had to control. So they had these rubber bands tested on the ground. They had them tested in near space at the same time. They tested them on black, they tested them on a silver surface. And they actually designed this, and we're using the terms controlled experiment, the control variable, and they knew what they were doing. So it was pretty cool, a good experiment.
Wow, that's amazing. That is really amazing.
And just it turns out to be the answer is an engineering answer that I needed to know. And they helped me discover it.
Yeah, what a great experiment. Well, thanks so much, Paul. We had a nice audience and lots of folks asking lots of questions. They loved, and lots of really good comments actually. And I know you can't see the feed. I'm looking at it though. People had all these really great comments. So they really enjoyed it. So yeah, thanks so much. I really appreciate it.
Well, thank you for letting me speak.
Yeah. And so I'm gonna end our stream now, but you and I hang out for just a minute here.
Okay.
Right, and folks, thanks so much for joining us. We really appreciate it. Look for the next talk on the first Friday of September. That would be September 4th. We'll have Professor Darcy Snowden from Central Washington University. 7:30 in the fall. So 7:30 in the evenings, first Friday. Have a great weekend, everyone. Stay safe.